Gnanam Paramam Dheyam. Knowledge is supreme.
Recall that last time we have proved that the Galois groups of cyclotomic fields in characteristic 0 as well as in characteristic P, they are in both the cases they are abelian groups, and these groups are connected to the unit groups of the ring Z mod n. So let me, I want to give you a few applications of this, and first of all I want to write down the last statement I proved, that if you have, so that I want to write it as a corollary. So corollary 1. So if I have a prime number P is a prime number, and suppose n is a non-zero natural number such that P doesn't divide n, then the Galois group of the cyclotomic extension Fp round bracket n over Fp, this Galois group is cyclic. Cyclic we knew it before, generated by the Frobenius of order P modulo n. This is the definition of order of the residue class of P in the ring n, ring Z mod n, and in this order is in the group Z mod n cross. This is the cyclic group of order M, which not order, this order which of order which divides this. When is then it is of order, when will this order will be 1, then this group will also be trivial. So order, and when will this occur? This occurs if and only if, so order of P n in Z mod n cross, this order is 1 if and only if the cyclotomic polynomial phi n has a 0, mod P equal to 0 in Fp for some integer, for some a in Z. And when is the order 1? That is if and only if that P should be congruent to 1 mod n, because we are reading everything mod n. So if the cyclotomic polynomial, this is a polynomial with integer coefficients actually, when I read mod that P and if it has a 0, for some 0 is in therefore Fp, if it has a 0 in Fp, which is equivalent to P congruent to 1 mod n, and that is then will imply the Galois group of the cyclic extension is cyclic. This cyclic Galois group is trivial, but that will mean that, so this is equivalent to saying Fp round bracket n equal to Fp. That means all the nth roots will lie actually in Fp. So that is the meaning of this corollary, and I want to use this corollary to prove some more results on Galois groups. Okay. So question is for which P this will happen. So that I want to state it as a corollary. Corollary 2. Corollary 2, as n is given any non-zero natural number, there exist infinitely many prime numbers p with p congruent to 1 mod n. So that means what? That means if I have given n and if I am looking for nth roots of unity for many p's, that fp will contain those nth roots of unity. So the phi n will have 0 there, not all of them, but phi n will have 0 in fp. Alright, so actually this will follow from the following. So proof. So I am going to give, we have given n. So we have given therefore phi n. Phi n is a polynomial in x with integer coefficients. And what do we want to prove? We want to prove there are infinitely many prime numbers p such that p is congruent to 1 mod n. That means we want to prove by corollary 1, we need to prove that for infinitely many primes, many prime numbers p, there exists an integer a with phi n a is congruent to 0 modulo p. Because this condition phi n has a 0 mod p is equivalent to p is congruent to 1 mod n. So I want to find infinitely many primes so that this polynomial has 0 in mod p. But this is very easy. So I will state a general interesting observation. So therefore the question becomes the following lemma. This will follow from the following lemma. So I have a polynomial f. F is a polynomial with integer coefficients. And the degree of f is bigger or equal to 1. So then there exist infinitely many primes prime numbers p such that f has a 0 in z mod p. So that means there exists an integer a in z with f of a is congruent to 0 mod p. So this means f bar of a bar is 0 in z mod p, where bar means denoting mod p. So if I prove this lemma, the corollary follows because we are going to apply this lemma to that phi n. So proof of corollary 2, apply above lemma to the polynomial f equal to phi n. And therefore, it is clear. So, I have to prove the lemma only. Lemma is very easy to prove. Let us prove the lemma. Lemma is very, very easy to prove. So, proof of lemma. What did you want to prove? You want to produce infinitely many primes so that f has a 0 mod p. Alright. That means what? That means, so I take a natural number x is a natural number, arbitrary natural number, non-zero, and I look at, I had a polynomial f in integer coefficients. So, I look at the value of f at x, so f of x. This is some integer and x is varying. So, there are many integers. So, look at these values, all the values. These are values of f. They are integers. I want to show that they have infinitely many divisors. So, these values have infinitely many prime divisors. That will produce, so if p is so this will prove the lemma, because if p divides f of x, that is equivalent to saying f of x is congruent to 0 mod p. So, this p is a required prime. So, if I values are the x is varying, then values are varying, but this set has infinitely many prime divisors. When I say this has infinitely many prime divisors, means there are prime numbers p infinite in number which divides fx for some x. So, therefore, that will prove the lemma. And how do you check this statement? They have infinitely many prime divisors. So, that is because, let us look at I am going to use the Taylor's formula. So, we are going to use Taylor's formula. I will recall that formula for the function f. F is a polynomial. So, f is you can think of f is a function from wherever, real numbers to real numbers. Any real number y, it is f of y. This is a polynomial function, so it is differentiable function. So, Taylor's formula makes sense. And what will be the Taylor's formula? Let us write down that. So, that means if I fix a, I will fix a is fixed, and Taylor's expansion at a I am taking. That means I have to write f of z equal to what? F of a plus f prime at a times what? Times will be z minus a. I am looking Taylor's expansion at a. Plus f double prime at a divided by 2 z minus a square and so on. This is a Taylor's expansion. Now, in this I am going to look at only the first term. So, that is f of a, and the remaining terms have z minus a as a factor, and this will not go on forever because f is a polynomial. So, this is actually a polynomial. So, this has only finitely many terms. So, from here I am going to take z minus a common, and what is inside then? F prime a plus f double prime a by 2 z minus a, and how long it will go on? It will not go on more than the degree. So once it reaches nth derivative of f evaluated at a divided by n factorial, and then z minus a power n minus 1, and after that the derivative will be 0. So the other terms will be 0. So it is this actually. So therefore, this I am going to use this. So how am I using it? I am using it to the following formula. So I am going to take z equal to f of z. I will take x plus, I have given, I take any x in natural numbers, and then take x and take f of x square. Then the Taylor's expansion of this will be, if you stare at it, it will be f of x plus f of x square y. This the remaining term I call. So I have taken what is clear. This is my a is my x and y is my z. See, I want, so once I adjust like that, you find suitable y, so that this expansion there. Now what do I want? I want, as x varies, this f of x has more and more prime divisors. So this is what? This is f of x times 1 plus fx times y. Now this is also value. This is also value of f. So this is the value of f. This is also value of f. But this value is fx times this, and this they are co-prime. You see, I have made them co-prime. So the prime divisors of this will be new prime divisors. So they are also prime divisors of this value then. So if I vary the values, then I am getting new and new prime divisors, and this is true for any x. So every time I will get a new value. So this one I have applied above formula to z equal to x plus f of x square. If I put above z equal to x plus f, this is this side, and a is x. So you see, this is that f of z, and f of x is f of a, and what is this term then? Z minus a. Z minus a is what? That is precisely this x will get cancelled, f of x square, and the remaining is y. So it is that. So that proves that, so this proves that when I vary, so varying x, we get new prime factors for f of x plus fx square. Any x is varying in n star, and then this is because f is a polynomial with integer coefficient, this is also integer, and then that is also an integer. So I get, these are integers and they have new factors, so that proves that, so this proves that there exist infinitely many prime numbers with p divides x for some x in natural numbers. This equation is equivalent to saying f of x is congruent to 0 mod p. That is, x bar in z mod p is a 0 of f bar in z mod px. That is what we wanted to prove. And we noted therefore that this we applied to f equal to phi n, the cyclotomic polynomial. So that proves that corollary. Alright, now I want to also note the following. this one, the last corollary, so what was the last corollary? There are, by corollary 2, there are infinitely many primes P with P congruent to 1 mod n. N is given. So, given n, natural number, non-zero natural number, we can find P so that P is congruent to 1 mod n. But how will the P look like? So, that means P will look like congruent to 1 mod n. That is same thing as saying, that is P is of the form 1 plus some multiple of n, where A is in integer. So, there are many primes with this condition, but that means they are in arithmetic progression. If you arrange these integers in an increasing order, they are in arithmetic progression. So, this is a very particular, this statement is a very particular case of the following theorem, which was due to Dirichlet's theorem in number theory. What does it say? It says that given two natural numbers n and m, both non-zero natural numbers, there are infinitely many primes prime numbers P with P is congruent to m mod n. And that means what? That is P is of the form m plus an, where n is an integer. So, the corollary 2 is m equal to 1 and n is any n. So, this is a difficult theorem. This is not so easy to prove, but it is a very fundamental theorem in number theory. So, we have proved very particular case of this, which is very useful for the Galois theory purpose. Okay, that was one comment. So, in characteristic 0, that is when I take k equal to q, this case, then what did we prove that? We proved that the Galois group of Qn over Q, this is a cyclotomic field extension. This Galois group is isomorphic in a canonical way to canonical is not the correct word here, because I compose with the automorphism group of the roots of unity, that is canonical, but identifying that with Z mod n cross, that was not canonical. So, this is not canonical, but anyway we know is an isomorphism here. This group is isomorphic to this group, that is what we proved in characteristic 0, and the proof, the main important step in the proof was to prove that this phi n, a cyclotomic polynomial, which is a polynomial with integers, this is prime polynomial in prime polynomial over Q, and that is therefore the irreducible, that is therefore the minimal polynomial of zeta n over Q. And we know this is a Galois extension, and Galois group also we know. Okay, now if I take any subgroup, so Z mod n cross, this group is the Galois group of cyclotomic field Qn over Q. So, if I take any subgroup H, then what can I do? Look at Q is here, Q power round bracket n is here, and I have taken the field now inside. I should call it L probably. L, this is precisely a fixed field of H under the action of fixed field of H Qn. See the Galois group, Gal Qn over Q, this group is operating on this field, and therefore, and H is a subgroup here. So this was Z mod n cross, H is a subgroup here. So I can take a fixed field. So the fixed field is in between. And in the fundamental theorem of Galois theory, we saw that this extension by fundamental, I will keep writing it, fundamental theorem of Galois theory, FTGT. This one, L Qn over L is Galois, is a Galois extension. And also, what is the order? Order of the Galois group. So, Gal of this, I think I have not checked this when I just proved they are bijective maps, but I will prove now that the Galois group of this or this is precisely H. No, that also you have checked. That also you have checked. So H, take the fixed field and go, then you get H is a Galois group. Therefore, H occurs as a Galois group of Qn over L. But now one may ask, what about this L over Q? Is it Galois? Is this extension Galois? And if yes, what is Galois group of L over Q? And I will prove in this case the answer is yes. And this Galois group of L over Q will nothing but Z mod n cross modulo the group H. Here the group H is subgroup, so it is a subgroup of an abelian group. So H is normal. So the quotient group makes sense. So I will answer this question as answer yes, and this Galois group is nothing but the quotient of the Galois group by the subgroup H. And this I will make it more precise in the next lecture. Lecture I will check that this extension is Galois and the group is the quotient. So that means we need to analyze in a under the Galois correspondence when will the fixed field will be Galois over the base field, and this will analyze this is if and only if the subgroup is abelian, subgroup is normal. This is what I will start doing from the next lecture. Also, I want to now decide which group occur as a Galois group over Q, and this is a very important problem. Still the answer is not completely known, and therefore it is of much interest, and next lecture I will say more things about this. Thank you.